archival footage of burning tankers from the 1980s tanker war, slow-motion simulation of a naval mine detonating under a hull, then cut to modern satellite imagery of the Strait of Hormuz, that impossibly narrow 21-mile pinch point between Iran and Oman. March 2026. Iran has effectively shut down the Strait of Hormuz, one of the world's most critical energy arteries. Carrying 1/5 of global oil and a huge slice of LNG, is now a no-go zone for commercial shipping. Insurance rates have skyrocketed, oil prices spiked, and the Pentagon responds by rushing thousands of U.S. Marines embarked on amphibious assault ships like the USS Tripoli and USS Boxer into the region. On paper, this looks like a straightforward show of force. But from a first principles engineering perspective, securing or reopening this waterway is an incredibly hard problem. Why? Because the physics of naval mines, anti-access/area denial weapons, and the unforgiving geometry of a narrow strait create a constraint that no amount of marketing or political rhetoric can wish away. For decades, engineers have known, in confined waters this tight, a handful of cheap, low-tech threats can create a high-tech nightmare. Today, we're breaking down the real military engineering challenges behind this deployment. Not the headlines, but the trade-offs, the physics, and the compromises that actually matter. Animated world map showing oil flow arrows converging through the strait, 21 miles wide at narrowest, with two 2-mile shipping lanes plus buffer. Graphs of daily throughput, 21 million barrels of oil, significant LNG, cut to global oil price chart spiking. Then overlay a Marine Expeditionary Unit, MEU, structure, 200-2, 500 Marines, air-ground logistics elements. The Strait of Hormuz is the ultimate maritime choke point. Its geography is merciless. At its narrowest, the navigable channels are barely 4 miles apart when you account for the traffic separation scheme. Every day, supertankers carrying millions of barrels must thread this needle, often within easy range of shore-based launchers. The driver here isn't abstract strategy. It's energy physics and economics. Modern civilization runs on dense, portable chemical energy stored in hydrocarbons. Disrupting even 20% of global supply creates immediate cascading effects on refining, transport, manufacturing, and food production. That's why the U.S. is deploying Marine Expeditionary Units, self-contained forces with infantry, artillery, aviation, and logistics that can operate from the sea without needing friendly ports. These aren't just troops. A typical MEU is a floating combined arms package designed for rapid crisis response. Seize key terrain, conduct raids, or enable mine clearance operations. The question is whether this force can overcome the fundamental constraints of the environment. 2:30 to 5:30, the physics constraint, the impossible barrier. Visual. CFD-style animation of water flow through a narrow channel, showing turbulence and restricted maneuver space. Slow motion of naval mine deployment from small boats. Ballistic trajectories of anti-ship missiles and drones from coastal positions. Equation overlay. Simplified drag and buoyancy forces on a mine versus detection probability. Let's think from first principles. Water is incompressible. Ships are massive displacement hulls governed by Archimedes' principle. They float because they displace their own weight in water. But in a strait that's confined, that creates a lethal vulnerability. Iran's anti-access strategy relies heavily on naval mines. Contact mines influence mines triggered by magnetic, acoustic, or pressure signatures. A single mine doesn't need to sink a warship. It just needs to make commercial insurers refuse to cover a $200 million VLCC tanker full of flammable crude. Physics makes mines brutally effective here. They can be laid quickly from small, fast boats that hug the coast, exploiting the shallow waters and high traffic density. Why is clearance so hard? Because detecting and neutralizing mines in littoral nearshore environments violates several engineering ideals. Sonar and magnetic anomaly detection suffer from clutter. The boundary layer near the seabed creates noise, multipath reflections, and false positives. Water's density, about 800 times that of air, means acoustic waves propagate differently, and temperature/salinity gradients cause refraction that bends signals away from targets. Mine-sweeping vessels must move slowly in predictable patterns to tow sensors or mechanical sweeps. That predictability turns them into easy targets for swarming small boats, drones, or coastal anti-ship missiles. The rocket equation doesn't directly apply. But the logistics do. Every hour spent clearing a lane is an hour the enemy has to remine or reposition. Add anti-ship ballistic and cruise missiles. These exploit the short flight times in a confined space, often under a minute from launch to impact. Radar horizon limitations and terrain masking from the Iranian coastline mean defenders have compressed reaction windows. Stealth helps reduce radar cross-section, but in such proximity, infrared signatures from engines and the sheer volume of low-cost threats create saturation attacks that overwhelm even advanced offenses like Aegis or phalanx systems. The core constraint: in open ocean, naval superiority wins through maneuver and standoff. In the Strait of Hormuz, geography compresses that advantage. You can't outrange what can be launched from a few kilometers away while staying hidden among civilian clutter. Exploded 3D model of an amphibious assault ship, LHA like USS Tripoli, showing well deck, flight deck with F-35B and MV-22 Osprey. Cut to V. 22 Tiltrotor transition animation, explaining proprotor aerodynamics. Simulation of marine raid. LCAC hovercraft landing. Infantry with engineering vehicles clearing mock minefields. Graph comparing transit times and fuel efficiency of Osprey versus traditional helicopters. So, how do engineers try to solve this? The U.S. Marine Corps' answer is the Amphibious Ready Group plus MU concept, a mobile sea base that does require fixed infrastructure. Ships like the America-class LHAs feature a massive well deck for landing craft air cushion, LCAC Hovercraft, essentially giant air cushion vehicles that reduce ground pressure to near zero, allowing them to cross beaches and surf zones that would bog down conventional landing craft. This exploits Bernoulli's principle in the cushion system. High-pressure air creates lift with relatively low power. Aviation is the real enabler. The MV-22 Osprey Tiltrotor combines helicopter vertical takeoff/landing with fixed-wing cruise efficiency. Why does it matter? Because in contested littorals, you need to project power quickly without exposing large ships close in. The Osprey's prop rotors tilt from vertical, helicopter mode, high disk loading for hover, to horizontal, airplane mode, lower induced drag. This gives it twice the speed and range of legacy CH-46/CH 53 helicopters, critical when reaction times are measured in minutes. F-35B style with short takeoff/vertical landing. Jets provide organic air superiority and strike from the same deck, using directed energy sensors and low observable shaping to reduce radar cross-section. The trade-off? Vertical lift demands enormous thrust-to-weight ratios, which hurts fuel efficiency and payload in airplane mode. On the ground, marine combat engineers bring specialized tools, explosive ordnance disposal robots, unmanned underwater vehicles for mine hunting, and rapid runway repair kits. The goal isn't to occupy Iran. It's to seize or neutralize key islands/terrain that dominate the shipping lanes, then establish temporary counter-denial zones with mobile anti-ship and air defense systems. This is clever systems engineering. Integrate air, sea, and ground elements so the whole is greater than the sum. But it's still bound by physics. Moving 2,500 Marines with heavy equipment across hundreds of miles of ocean requires massive logistical throughput, governed by fuel energy density and ship displacement limits. Side-by-side comparison graphs. Osprey speed/range versus fuel burn rate, showing 3x higher consumption in hover. Mine clearance timelines from historical data, slow and incomplete. Cost overlay. Annual operating cost of 1 ARG/MEU. Animation of saturation attack, overwhelming CIWS. Nothing here is magic. The Osprey is faster, but it burns significantly more fuel in transition and hover modes due to higher induced power requirements. Amphibious ships are vulnerable in confined waters. Their large radar signatures and limited maneuverability make them high-value targets if air cover slips. Mine clearance remains painfully slow. Historical operations show that even advanced systems achieve only partial clearance rates, leaving residual risk that deters commercial traffic. Swarming low-cost drones and missiles exploit the economics. Cheap attackers versus expensive interceptors. 1 SM. 6 missile costs millions. A basic drone can cost thousands. Saturate the defense and physics. Conservation of momentum, reaction time. Favors the attacker in close quarters. Skeptically, claims of rapid reopening often gloss over these realities. A full clearance operation could take weeks, not days, with constant recontestation possible. Ground elements add risk of escalation and casualties. Urban or coastal fighting in this terrain amplifies the fog of war. Cost-benefit bar chart. Daily global economic costs of closure versus estimated military operation expenses. Long-term graphs showing alternative pipeline/canal concepts and their massive infrastructure hurdles. Final shot. Clean animation of oil flowing freely again, but with question mark overlay. Is this deployment viable? Short term, yes. It provides options for limited raids, escort operations, and deterrence that pure air or naval power can't match in this geometry. Long term, it's a stopgap. True resilience would require diversified energy systems and alternative routes, but those face their own physics and capital constraints. Pipelines have throughput limits. New canals are civil engineering nightmares on steroids. Economically, sustaining a large amphibious presence here is expensive. Fuel, maintenance, personnel rotation. In the billions annually. It works only as long as the political will and industrial base support it. Cheap mines and missiles remain asymmetric levers that physics hasn't fully neutralized. Visual. Montage of historical engineering breakthroughs, Hovercraft, Tiltrotors, stealth, dissolving into the unchanging narrow blue line of the strait. Fade to human silhouette against a physics equation backdrop. The Strait of Hormuz reminds us that human ingenuity can push against the limits of nature, building machines that defy gravity and drag in clever ways. But it cannot repeal the underlying laws. Geography, fluid dynamics, and energy trade-offs still rule. The Marines rushing to the region embody that eternal engineering loop. Identify the constraint, design around it with compromises, and accept that perfect security is an illusion. In the end, the real solution may not be more steel in the water, but smarter ways to reduce our dependence on any single vulnerable artery. Nature doesn't negotiate. We adapt or we pay the price. Thanks for watching. If you want a deeper dive into Tiltrotor aerodynamics or mine countermeasures engineering, drop a comment. Subscribe for more first principles breakdowns of the technologies shaping our world. Sources subscribe. Related videos on naval engineering, energy systems.